So now we want to look on a really interesting example where we really can see what all those things mean, namely the momentum operator, which corresponds to taking the derivative. So this is our main example where our operator T is the operator which usually we denote by P, which is the momentum operator. So this corresponds in physics to measurement of the momentum. Okay, but anyhow, we only care about mathematics at the moment. So my operator T is I times taking the derivative. So the I, we need to make it at least formally symmetric. Or maybe let me just write it more compact. It's I times f prime if I apply T to function f. Yeah, and so we have to work on a Hilbert space. Our Hilbert space is the L2 space. And now, of course, we can make choices whether we take a closed interval, all of R or R plus. And I want to take here the compact interval. So let's say from 0 to 1. So H is the L2 space, square integrable functions. Functions defined on the interval 0 to 1, of course going to C. And now, yeah, we want to take derivative of such functions. So we have now to put a domain for our operator. And of course it is clear we cannot just take all L2 functions, but we must take functions which are at least in some sense differentiable. And let us start with maybe the most canonical choice, namely take functions which are differentiable, and maybe just to be sure also assume that they are continuously differentiable. Because then, of course, this is maybe the nicest thing. Maybe we could even take C infinity functions, but this here will probably be enough. So let us put as a domain the straightforward thing, just taking the functions for which we are sure that we can take the derivative, and we have all the nice rules for working with the derivative. So we say those are the functions in L2, but not all of them, but they should be differentiable, and we even assume continuously differentiable. So the derivative should also be continuous, and then we also need some boundary conditions. And you will see quite soon we need this to ensure the symmetry of our operator. So we also assume that at 0 and at 1 we have boundary conditions, and we require that the functions should be 0 at both ends. Okay. And of course boundary conditions will be the issue. We will come back to this. Yeah, but now let us first see that this is a good definition. So I mean, of course, this space is a linear subspace. And the operator is defined on this subspace to the whole Hilbert space, because if I take the derivative of a continuous function on this interval, then the image is again in L2. Of course, the image should be in L2. But because we assume it's continuously differentiable, so it's continuous on this compact interval, so it's again in L2. Good. But now let us check that this indeed is a symmetric operator. So we say T is symmetric. And this is of course now just a formal, formally this is clear. And this is what is easy to check. So what we have to see is that in the inner product I can bring T from one side to the other for all vectors which are in my domain. So this means I have to check for functions f and g in the domain of my operator that in the inner product tf, g, I can bring the t to the other side. Okay, but this is now, of course, just partial integration, but let us do it quite detailed. So the L2 inner product, of course, is we are integrating from 0 to 1 over this function, the complex conjugate. T of f is I times f prime. Or we take the complex conjugate, we multiply this with g of t, and we integrate. That's our inner product. And now we have to see that essentially we have to move the effect of t to the g. So we have to move the derivative to the g, and of course this is partial integration. But maybe let me first take out the I. under the complex conjugate sign, it comes out with a minus sign. So I have here actually minus integral from 0 to 1 f conjugate prime of t g of t dt. And now I do partial integration, which means I can move the derivative from here to here, getting a minus sign, and then of course I have boundary terms. And that's of course the things which should vanish, and which are the reason that I have to put conditions on the boundary for my functions. Yeah, okay, but so with partial integration, I get the prime on the other side, changing the sign here. So I have here plus I integral from 0 to 1 f bar of t g prime of t dt. And then I have the boundary condition, so I have the minus I, and I have to take f bar times g at the boundary 0 and 1. So I have to take this at 1 minus this at 0, which means this here okay, let me continue here. Oh, maybe let me write it down here. Also this here, let's say without the I, so this is f bar of 1 times g of 1 minus f bar of 0 times g of 0. And now for f, also for g, I have required that they are in the domain. So this means at 0 and at 1 they are 0. So this means this here is 0, this here is 0, the whole thing is equal to 0. So this term goes away, and I'm really left with the inner product where t acts on the other side. So I'm really left with the first term, which is the integral from 0 to 1. And now I move the I inside again, because the t also has this I in its action. So I have here yeah, the f bar of t, and the I, I'm writing it here, g of t, and you see this here of course is now just the action of t but on g. And of course we assume that g is also in the domain, so this makes sense. And what I have here is just the inner product between f and tg. So you see this is just partial integration with the right choice of the boundary conditions, so that we can move the integration from f to g. Yeah, and so this tells us this is a symmetric operator, so it's at least a nice operator. In particular, we know it's closable. So this here shows the operator is symmetric. So T is a subset, or yeah, T star is an extension of T. But the question is, yeah, is it now self-adjoint or essentially self-adjoint, or what is T star? So that's the crucial question. And probably it is clear, or maybe you can imagine that it will not be a self-adjoint operator, because the domain here is chosen maybe too small. But we have to see what this means. In particular, we should see how do I now really calculate the adjoint. That's a crucial thing. So yeah, so let us take an element in the domain of T star. And what does it mean? So how is the domain how is the domain of the adjoint of an operator defined? So it means we must find an H, which then will be the T star of G, such that this H has the property, if I'm looking on the inner product G TF, I can bring the T on the other side, and what appears here is this T star of G, so it is this H. So I must have such a vector H, which I can write on the other side. So I must be able to write this as H, comma F, for all F's where this makes sense, and this makes sense if F is in the domain of my operator T, for all F in the domain of T. So that was how we defined the adjoint of an operator. And maybe when I defined it, I wrote the other way around. It doesn't matter, but maybe it's nicer to have the things linear on this side in the F. So it's the same. Good. Okay. And so now we should check what this means. So we're looking on a G. We don't know. I mean, we want to find out what are the properties of G, such that such an H exists. Okay. And of course, I mean, if G is in the domain of t, then what we did before shows that it is okay. But there could be more, a bigger domain of t star. And that's what we really have to determine. So this here means, yeah, what does it mean? Let me write down this equation. So this inner product here, so this is g of t bar. Then the effect of t is taking I times the derivative, and then I'm taking the inner product. So this here, this is just this inner product, and this has to be the same as the inner product on the other side, which is the integral over my function h, and then I have here f of t dt. Yeah, and so you see, I have somehow to see that I can bring the prime from this side to this side, but at the moment, I mean, I'm not sure. I mean, I'm not sure what to assume of g. So at the moment, I cannot assume g has all the nice properties so that this is possible. So I have to argue now in a way. In the end, I would like to see what g is, and if I bring it on the other side, I should have the g prime, but I cannot use that I already know that taking the derivative of g prime is possible, and I have the partial derivative. So the argument must work in a way, and that's why I'm introducing this h, which in the end should be the g prime, but at the moment I don't know this. So I have to somehow argue in this general way. Yeah, and how can I do this? Yeah, I mean, I do this in a way, first of all, so what I have here should be the derivative of something. In the end, it should be the derivative of g, but at least the point is that I would like to write this as the derivative of something such that I can use partial integration on this side. So this means I write now, I have here an element, so h is an element in the domain of t. So no, h is, okay, h, I don't know what this is. H can be a general element in the L2 space, so I don't know anything about h, but nevertheless I can write it as a derivative of a function capital H almost everywhere just by taking the definite integral. So just by defining this h of t here as the integral from 0 to t over the little h ds. Okay, h is a L2 function, so it's integrable, so I can define this capital H. So this is well defined. I mean, integration is a very nice mapping. Taking the derivative is the not so clear thing. Okay, so we go here the other direction. So I write this h as a derivative of something. That's something which I can always do by just taking this antiderivative or indefinite integral. And then I can now continue here my calculation from here. So what do I have then? So let me write it down again, or maybe just continue. This is what I have there. So on this side, so I write this now as the integral, and this little h I'm writing as a derivative of the capital H. So this is, and I have the complex conjugate here, so this is a derivative of h, f of t dt. Yeah, and now, of course, I would like to do again partial integration. So I have the derivative of a function and the function f here. F is a nice function, so this is okay, but this h, of course, so this h has a derivative, and this h is now a nice function. It's continuous, it's actually absolutely continuous, and this h is now a function for which I really can do partial integration. Okay, so yeah, so if I take the indefinite integral of a function, I get a nice function, actually a function which is absolutely continuous and for which the partial integration result, I mean, actually the fundamental result of calculus, that if I take the integral over the derivative is the integral again. Okay, so if you don't know this, I will in a extra video lecture, I will give a short survey on the results about integration theory, but in particular also about absolutely continuous functions and addressing also exactly this issue. But so here I'm just using this fact that this H is absolutely continuous, which means in particular that also H times F is absolutely continuous, because F is it's nice anyhow, so I can use the partial integration here. So this here is really, again, minus h bar of t times f prime. So I can bring the h, the derivative from here to here, dt, and then I have again boundary terms, and the boundary terms are now h times f. So I have h bar of 1 times f of 1 minus h bar of 0, f of 0. And f now is in the domain of my operator, so that's the functions for which I require those boundary conditions. So f of 1 and f of 0 is equal to 1. So these boundary terms again go away, and now I really have moved the derivative just to the other side without having any additional terms. So maybe let me continue here. Yeah, so what I have is that this is the same as this, and what is the goal? I mean, our goal is still to see what condition this gives us for the G. What condition does this give us for the G? And you see we have here condition involving the f prime for all f's in the domain. So let me put this out, this f prime. So I'm writing this, bringing this on the other side, and then I have f prime of t, and here I have I times g bar of t. This on the other side is plus h bar of t dt. So this is equal to 0, and we know this for all f in the domain of t. So this means here I have the guys in which I'm interested, about which I want to learn something, and they have a property, namely that if I multiply them with the derivative of functions in my domain of t and integrate over them, then this should be equal to 0. So this means this guy here is orthogonal to all those f primes. So the I g bar plus h bar is in the orthogonal complement of the f primes. And you might first think, okay, I mean, if I would have the f here, then it would be in the orthogonal complements of my domain, which is just 0, because my domain is dense. But here I'm taking the f primes, and because I also have those boundary conditions. If I'm looking on the derivatives of such functions, this is not dense, but it's almost dense. But there is an orthogonal complement, and this guy, which I'm interested here in, is in this orthogonal complement. So what I have is this guy here. This is in orthogonal complement of the derivative of the functions which are coming from my domain of t. This orthogonal complement, and if you think a little bit about this, this is actually multiples of the identity. Okay, so this thing here is not dense in the L2 space, but there is missing the multiples of the 1, because it's the effect of taking the derivative here and also having a boundary conditions. So maybe this is something which you should think about. This is quite easy to see, but maybe in an assignment we can think about this. Okay, and so this means that this guy here is actually a constant. So from this we get that this here is a constant, or to put it another way, that this g bar is equal, if I bring this on the other side, is equal to I times h bar plus a constant. Yeah, but now we see that the G is still the unknown thing about which we want to find out what properties it has. It is now the same, up to a constant, as this H, and this H was defined as the indefinite integral. And indefinite integrals are nice functions, so namely they are, as I already said, almost continuous, absolutely continuous. They are absolutely continuous, and so we see here that this g bar must be an absolutely continuous function. So this guy here is an absolutely continuous, which I will usually abbreviate by AC, continuous function. So absolutely continuous functions are continuous functions, but they have a stronger property. Absolute continuity is stronger than continuous, but it's exactly the right property which ensures that the function is differentiable almost everywhere, and that actually you have the fundamental theorem of calculus that if you are integrating the derivative of this function, you are getting back the function. Okay, I will say more about this in this extra video about those things. But this is really a nice class of functions, but it turns out here that this is exactly the condition which we need for G. And I mean, this is a weaker condition than asking that we have a continuously differentiable function. Because here we really started with functions which were continuous, which are differentiable everywhere, and the derivative is continuous everywhere. So this is a very strong thing, which of course in the L2 setting maybe looks much too strong. It is clear that we don't have to require those things everywhere. We just need almost sure differentiability and things like this. And it turns out that the class of absolutely continuous functions is exactly this class. And that's what taking the adjoint gives us here automatically. And you should also notice that for the G, we are not getting any boundary conditions here. So, yeah, we have here, so we get here as a condition for our G that it should be absolutely continuous and no boundary conditions. And of course, what is the effect of the operator t? Again, from this we see it's still taking the derivative. So what do we see? So maybe first note no boundary conditions. For G. And so what is the T star of G? So the G's for which okay, it's not there anymore. So the G's for which we get this H, those are the absolutely continuous ones, and of course the T star of G is exactly this H, which we had there. Okay, but this H is related with this capital H by the fact that H is a derivative of capital H. Yeah, and here we have the relation between G and H. So G is essentially this capital H up to this I. So this H here, the derivative of this, is the same as the derivative of G, almost everywhere. So this here is I times G bar. So you see that the T star on G is still taking the derivative. But now for a bigger class of functions, the G's are now not just, as we started, continuously differentiable functions, but here they can be absolutely continuous functions, for which taking the derivative still makes sense in an almost everywhere sense. So maybe one should here note explicitly that almost absolutely continuous functions are almost everywhere differentiable. So this here makes sense. So what we have seen here is that the domain of T star consists of functions which are absolutely continuous. I mean, at the moment we have not really seen that the domain is equal to this, because I mean we only have seen here what does an element G in the domain of T star has to satisfy, and we saw it has to satisfy, it must be absolutely continuous. So let me write here, it's a subset of the G's, which are of course in L2. G should be absolutely continuous, and of course the derivative, so absolutely continuous guarantees that the derivative exists almost everywhere. So we have a G prime, but of course the G prime must also be in L2. In this setting here, this was coming from the fact that we required that the derivative is a continuous function. But here, this is not clear, so this is an extra condition. So the G prime is of course dh, and dh was required to be in L2. So this is clear, because I mean the effect of T star on G is taking the G prime, and so this should be an L2 function. So we need this as an extra requirement, but we don't need boundary conditions. So here you see there are no requirements on the boundary conditions, because in the partial integration these boundary terms go away, because we have on the f we have the boundary conditions. So for the h here, we don't need any condition here, because we know that f of 1 and f of 0 are equal to 0. Yeah, okay. So that's the domain. Well, it's contained there, and actually we have here equality. And this is quite easy to check, just calculating the other way around, taking a function g which has these properties, and then just doing the calculation here again. And then you see that actually we have here equality. Okay, so just by direct checking. I mean, showing that this is a subset, that was really the harder part, because there we had to calculate with the g without knowing a priori that we can take the derivative of g. If I start with a g with these properties, then I know that I can take the derivative, and then I just do the partial integration. But for the other way around, I only know I have a g, and I don't from the beginning I only know it's in a L2 space, and then I have to see by doing those calculations that it has a derivative, but this only shows up at the end, because then I know it's equal to h, which has a derivative. Okay, so this we get by direct checking, and all this together shows us now that what we have here is an operator which is not self-adjoint, because here we see that the domain of the T star is much bigger than the domain of our operator T. So first of all, instead of having continuously differentiable functions, we have absolutely continuous functions, and then we have also got rid of the boundary condition. So this means what we see here is that T is not T star. T star is of course an extension of T. Of course, I mean here the domain of T star is much bigger than the domain of T, but T is not self-adjoint. So it's really different here, and so T is not self-adjoint.